This video discusses Descartes' rule of signs and upper and lower bound rules. These two techniques that we're going to discuss are techniques to help us make educated choices on which of our possible rational zeros to test. It's possible that we could have a list of 40 numbers, 100 numbers. We don't want to have to do synthetic division for 100 numbers, so if we can narrow down the list, that would be really beneficial to us. So the first technique is Descartes' rule of signs. Descartes' rule of signs says if a polynomial function has real coefficients and the constant term is not zeros, then the number of positive real zeros of the polynomial is either equal to the number of sign variations in p of x or less than that by a multiple of 2. And a sign variation is just when it switches from plus to minus or minus to plus. The number of negative real zeros of the polynomial is either equal to the number of sign variations in p of negative x or less than that by a multiple of 2. I can further explain this as we work through a problem. We're going to be creating a chart that represents the possible combinations of zeros for a polynomial. Our options for types of zeros that we could have are positive reals, negative real, or complex. Those are our choices. We're either going to have real answers or complex answers, but then we can be more specific about the reals and break it up into positives and negatives. And we're going to be making a chart. Descartes' rule of signs says that the number of positive real zeros is equal to the number of sign variations in p of x or less than that by a multiple of 2. So let's take a look at p of x. How many times does it switch from plus to minus or minus to plus? Well, it only happens one time, right here. So our first option for positive real zeros is that there could be one. And now I'm going to write this above my heading because there could be another option. Our rule of signs says that it's equal to the number of sign changes or less than that by a multiple of 2. Well, if I subtract 2 from 1, I would get negative 1. We're listing a quantity here. How many positive real zeros? When listing a quantity, a negative number doesn't make sense. You would never look in the fridge and say, oh, I have negative 1 gallons of milk in there. You might say 0, so 0 would make sense, but a negative quantity doesn't make sense. So that second option isn't an option for us. You may be asking yourself, why are we subtracting 2? Why is it less than that by a multiple of 2? The reason that we could possibly be decreasing a type of 0 by 2 is because of the possibility of a complex pair of zeros. Remember, our imaginary zeros theorem says that complex zeros always come in pairs, in twos. So when we're subtracting by a multiple of 2, we're subtracting out complex pairs for our additional options. All right, we only have one option for positive real zeros, and that's 1. Now we have to talk about the options for negative real zeros. Descartes' rule of signs says that the number of negative real zeros is equal to the number of sign changes in p of negative x or less than that by a multiple of 2. So we need to find p of negative x. We're replacing all of our x's in p of x with negative x. And then we'll simplify. We have negative x raised to the fourth power. A negative raised to the fourth is a positive. So that's going to be positive x to the fourth. Next, we have a negative raised to the third power. Negative x raised to the third is a negative x to the third. We have negative x squared. A negative raised to the second power is a positive. So we're going to have plus x squared. Negative 8x minus 12. We can clean this up a little bit more with that 2 times negative x to the third, and we get that p of negative x is equal to x to the fourth minus 2x to the third plus x squared minus 8x minus 12. There is a little shortcut to finding p of x if you're interested. Because of this whole even-odd rule and raising a number to either an even or an odd power, you can get p of negative x directly from p of x. All you have to do is change the sign on the odd degreed terms. The even degreed terms are going to stay the same because when you raise a negative to an even power, you get a positive. But the odd degreed terms change sign. If you don't feel comfortable with that shortcut, just do it out the way we did here. All right, how many sign changes do we have? How many times does it switch from plus to minus or minus to plus? We have 1, 2, 3 times. Our first option for negative real zeros is going to be 3. Our rule of signs says the number of negative real zeros is equal to the number of sign changes, or less than that by a multiple of 2. Now that we found our first option, we want to start subtracting multiples of 2. If I subtract 2 from 3, I get 1. Is 1 a number that makes sense when we're talking about a quantity? Yes, it does. So we have a second option for negative real zeros. Now we're going to subtract 2 a second time. 1 minus 2 is a negative 1. Does a negative number make sense when we're talking about quantities? No, it does not. So that is not an option. Our only 2 options for negative real zeros is 3 and 1. Once you've gotten your options for positive real zeros and negative real zeros, we can start filling in our table. We'll start with the first 2 columns. We want to do every possible combination of positive options with negative options. I almost think of it like I'm distributing when I'm doing these possible combinations. So I'm going to do 1 with 3, and then 1 with 2. 1 with 1. To get the numbers that go in our complex column, we're going to go back to our n-zeros theorem. We know by that theorem that the number of zeros is equal to the degree of the polynomial. Each one of these rows has to add across to be the degree. To fill in the complex column, we're just going to figure out what number we would have to put there so that each row added across to be the degree, which in this example is 4. Our first row, we already have 1 and 3, so what would you add to that to make 4? 0. In our next row, we have 1 and 1. What would we have to add to that to get 4? 2. Our zeros, if we were to find them for p of x, would either end up being 1 positive real, 3 negative real, and no complex, or our zeros would be 1 positive real, 1 negative real, and 2 complex. How does this table help me make educated choices on which possible rational zeros to test? Well, our rational numbers are real numbers, so we're only looking at the first 2 columns for guidance. You want to avoid columns that have zeros in it, because then there's no chance of having that type of number, so let's just avoid no chance. So my first recommendation, avoid the columns that have zeros in them. If no columns have zeros in them, or they have the same number of zeros in the columns, then I recommend choosing the column that has the greatest number in it. So if I was looking at this chart and going to start testing possible rational zeros, I would start with negative numbers because 3 is the largest number in the first 2 columns. I also want to mention that your complex column should always be even numbers. Remember that complex zeros come in pairs, in twos, so that column needs to be a multiple of 2, which would be an even number. The other rule that we have to help us is our upper and lower bound rules. This is something that you kind of just need to remember, and when you see it, you can help it guide you. If we let f of x be a polynomial with real coefficients and a positive leading coefficient, suppose that f of x is divided by x minus c using synthetic division. So, all right, we're set up for synthetic division. We do synthetic division. Now we're going to be looking at the results of the synthetic division. If c was positive, so if your zero that you were testing is positive, and each number in the last row, which is your quotient, your coefficient or your quotient, is either positive or 0, then c is an upper bound for the real zeros of f. So basically, if the 0 you're testing is positive, and after you do the synthetic division, you don't get a remainder of 0, all the numbers, or even I guess if you did get a remainder of 0, all the numbers on the bottom row are either positive numbers or 0. That means the 0 you're testing is an upper bound. Therefore, the next number you check should be lower than that number. The other one is when the 0 we're testing is negative. If c is less than 0, and the numbers in the last row alternate between positive and negative, 0 can count as either positive or negative, then c is a lower bound for the real zeros of f. So if you are testing a negative 0 using synthetic division, your bottom line, the coefficients of your quotient, if they alternate between positive and negative, and maybe there's a 0 in there, then c is a lower bound for the real zeros, and you want to check zeros larger than that. These are a couple rules that can help us make better choices on testing our list of possible rational zeros.